And I'm going to talk briefly about features of the standard so that if you're going to work with it, you'll have somewhat of a understanding of what's going on or what are the pros and cons to use it. So we talked a little bit about channels and allocations of channels into lanes. So Interlaken has a flexible number of lanes that it can map data onto, which is really fantastic. And it can map onto those lanes data from multiple different channels. And these channels can have different bandwidths. It can be very high-speed data or very sparse data like control data or some other. And Interlaken will take care of merging those data packets together and sort of sending them on a set of common lanes. And the encoding there is 64B, 67B. It's a little bit odd, but at the time it was cutting edge, I believe. So 64, 66 wasn't as well established, but this additional bit on top of the 66 has a meaning for it's an inversion bit, so it allows you to control the running disparity of the data. So there are two control bits and a inversion bit added on top of every 64 bits. And this data is mapped into bursts, so packets are split into burst-sized pieces to be sent across links. So there are two parameters that control the burst size in Interlaken. One of them is burst short, which defines the shortest burst that can happen. So it helps with processing multiple bursts at once inside of the design. So you control what is the smallest amount of the burst. And the burst max controls what is the largest size of the burst. And this helps with like retransmit buffer sizing or receiver buffer sizing, basically for processing this data. And we'll get to the diagram on the bottom in a second. I just want to mention also this Lucas I that I mentioned before. It is an alternative operation mode that has less channels and allows for shorter bursts. Because in general, like in the basic Interlaken, the shortest burst is 32 bytes. But if you want to have shorter bursts, you can use this Lucas I mode. Right? And then in this drawing, we have basically an indication of how data is mapped together with control words. You can see in these vertical columns, it's 67 bits, so basically one Interlaken word. There are burst control and idle control words, and also the B numbers are basically packet payload bytes. So here we're sending a packet of 70 bytes, but we have a burst max set to 64. So the payload doesn't fit into a single burst. And I wanted to demonstrate how the data is split into a second burst and what happens with the second burst if the data doesn't fill it completely. So in the headers in the orange and yellow, you can see different encodings for if it's a control word or a data word. In the burst control, there are specific bits that sort of have information about the burst, but I'll get into that later. It's followed by data, and after the burst max is reached, there will be another burst control word that sort of indicates data for the next burst. And once we fill all of the data, we'll start padding it with sort of fill bits. And once we fill into a whole Interlaken word, the next one will be an idle control word with an indication of an end of packet and how many bytes actually are filled in the previous word. And because the burst short is set to 32 bytes, you'll have to have padding for the next 3 control words just to sort of fulfill the burst short requirements before we start sending new data. And these sort of Interlaken words that are presented here can be mapped over a varying number of lanes, and they're sort of mapped in a round-robin fashion so that no single lane is unused or does not transmit data. So if you have active lanes, you will spread the whole data burst across all of those lanes. So on the bottom, there are two examples of a 3-lane configuration and of a 2-lane configuration, indicating into which lane which Interlaken word will be split and sent. And that was a short introduction to the data mapping. And now I'm going to talk about data integrity aspect. And this is a very big part of Interlaken. So we have mechanisms for error detection. And we have a CRC24, which sort of covers the data burst. And inside of the burst control or idle control word, there's a space for a CRC. And the CRC covers the payload plus the control word, or the upper bits of the control word, up to the CRC value, without those 67 or the 3-bit headers. And for the CRC32, this is a CRC that is sort of calculated on a per lane basis, because previously the burst is spanned across multiple lanes. So this is sort of like a data integrity CRC. The CRC32 is more of a diagnostic CRC to help you identify if a specific lane is acting up or has like a link fault, so you can quickly know which specific lane that is and maybe take it out of commission. And there's an additional CRC4, which is used for protecting out-of-band flow control, an out-of-band flow control interface, because it is a separate interface with separate pins that needs sort of a error detection mechanism as well. And besides the error detection, we have an extension for error correction, which is the RSpec 544514, which is pretty common, I believe. It can correct 15-symbol bursts, so up to 141-bit long bursts of errors, and it's necessary when doing PAM4. And this error correction, the read-solve forward error correction mechanism, is sort of placed outside of the base Interlaken, so it's like an add-on which sits between the Interlaken and the PHY and does some recoding of 67 into 65 bits, and basically it aggregates data from 2 Interlaken lanes into a single FEC instance to calculate the parity, and also correct on the other end from a pair of lanes. So when using the FEC, you have to deal with a multiple of 2 number of lanes. And finally, the retransmit, which is a way of Interlaken self-correcting these errors, they occur. So if a CRC24 checker indicates that there's an error in the burst, in a data burst, it will ask to the transmitter through the out-of-band flow control for a retransmission. And how that happens, basically, the transmitter keeps in a transmission buffer a copy of the data that it has sent. Some amount of data overriding it continuously. And at the point where the receiver will ask for a transmission, the transmitter will just basically stop the normal data path and start sending data out of the retransmit buffer. And it is the receiver's sort of role to find the point in a packet using some indexes where the error occurred, so the last known good burst, and pick up the transmission from there. And in that way, it can recover from error occurring on the transmission lanes, basically by the transmitting sending everything over again and the receiver picking up whatever it needs from that traffic. And now I've talked a lot about the flow control, and maybe now I'll go into more details of it. So Interlaken has 2 mechanisms for flow control, which is quite interesting. One of them is in-band flow control. And this in-band flow control is used when you have a duplex implementation, right? Because it uses the data lanes and some bits inside of the control words to carry the flow control information. And it needs to be a duplex, a bidirectional link, so that the receiver has also a transmitter path to communicate to the other side flow control information. If you are doing a simplex type operation where you only have a transmitter and a receiver on both ends, so one side can only transmit, you would use the out-of-band flow control interface, which is a set of separate pins that can communicate from the receiver to the transmitter the flow control information. And the flow control information is basically a 1-bit on-off sort of indication, plus some CRC that protects this data. The dual calendar extension we mentioned before also deals with flow control. So normally the set of on and off bits is called a calendar, and with dual calendar you keep a second copy of that, and it's called a shadow one. So there's an active one, and then there's a secondary that's a shadow one that you can modify while the link is operational, and then at a single instance in time switch the active for the shadow. So basically change the configuration while it's running. And finally, a very important part of Interlaken is rate matching. So the ability to slow the transmitter down in order to run at the speed of the receiver or the receiver's interface. And in this example here on the bottom, you can see we have an upstream device that has a 24 gigabit per second Interlaken sort of interface, and then a secondary interface device that interfaces between Interlaken and maybe 2 SPIs, and those SPIs would be running 10 gigs, so they have a total bandwidth of 20. And it would be sort of the designer's role to know that you need to sort of match these, if you don't want flow control to kick in, to match these rates by setting up some registers, so you can instruct the upstream device to only use 20 of those 24 gigs of bandwidth, basically inserting some idle control words into these bursts, right? And another example is if you just have an application interface that is running slower, you can also limit the upstream device.